Section. Introduction. We're diving into the fascinating world of large language models, LLMs, a rapidly growing field of research with applications in various sectors, from cybersecurity and finance to law and healthcare. Researchers have been working tirelessly to enhance these models, focusing on aspects like latency, ethics, and evaluation. This has led to the development of unique techniques for LLMs, such as prompting and in-context learning, ICL. Prompting is a fresh approach where we use text prompts to model tasks that are usually solved during pre-training. This has given birth to a new area called prompt engineering, which is all about finding the right prompts. Several prompt engineering methods have been developed, including input-output, I/O, chain of thought, COT, tree of thought, TOT, models vote, MVP, and self-consistency, SC, prompting. Generative LLMs make predictions based on the given prompt, which is the context. This creates a natural link between prompt engineering and ICL. The I/O prompting paper introduced Instruct-GPT, a model trained to follow instructions, which was one of the first works to showcase and popularize ICL. ICL is a learning method that uses a given context to learn and make predictions. It's a post-training approach that doesn't require parameter updates, making it a popular strategy for interacting with LLMs. Recent studies have shown that ICL can also be seen as a higher-order function that can construct inputs from labeled input-output examples. While LLM advancements have spurred ICL research, our understanding of ICL and its capabilities is still limited. Few studies have explored the relationship between ICL and specific properties of the function it tries to approximate. In this paper, we propose a new ICL task, approximating functions with a varying number of minima. We implement a function that transforms its inputs into another function with the given inputs as minima. We also compare the performance of ICL to that of a two-layer neural network, 2NN. Our contributions include proposing a new ICL task of approximating functions with varying number of minima. Our experiments show that increasing the number of minima reduces ICL performance. However, ICL still outperforms 2NN across various configurations. We also present a general approach for producing functions with the given minima. Lastly, we provide the codebase that fully reproduces the results in an intuitive manner. The success of LLMs has led to both theoretical and experimental studies on prompt engineering. I/O prompting is a simple method where one or more examples are given to the language model before the final query. COT prompting uses a series of reasoning steps to guide the LLM to the correct output. TOT builds a tree out of prompts that can later be navigated using algorithms like breadth-first search, BFS, and depth-first search, DFS. SC and MVP are both ensemble prompting approaches. SC prompts the same model multiple times, while MVP prompts multiple models once. Automatic prompt engineering approaches have also been proposed, but some studies found that automated prompting does not consistently outperform manual prompting. ICL is a new area of research, and several studies have been conducted on the topic. Some researchers have investigated ICL by approximating simple function classes, showing that the data and input dimensionality can significantly impact ICL performance. They also found that curriculum learning improves training and leads to faster convergence. Other studies have considered linear functions in their study of ICL, proving that transformers can implement learning algorithms for linear models based on gradient descent and closed-form ridge regression. Some have explored the interplay between compositionality and ICL, demonstrating that storing intermediate multi-layer perceptron, MLP, layer outputs improves ICL performance. Others have examined ICL performance on linear regression while varying the diversity of tasks in the pre-training dataset. In this paper, we use the formal framework introduced by previous researchers. Using this framework, we develop the theoretical and experimental setup for the study. A model can in context learn a function class if it can approximate most of the functions in that class. We define a prompt and suppose that an LLM can in context learn a function class up to a certain level of accuracy. With this framework, we can define and evaluate specific functions and function classes. Section Summary. The section introduces the concept of in-context learning, ICL, in the context of large language models, LLMs. Prompt engineering is a technique used in LLMs where textual prompts are used to model downstream tasks. ICL is a post-training approach that relies on a given context to learn and make predictions, and it has shown to outperform other methods like two-layer neural networks, 2NN, in various configurations. Section: Producing functions with varying number of minima. We're going to explain how to create a function with a specific number of minimum points. This is done by combining simple functions to form a more complex one. This idea was first inspired by a post on cross-validated, and we've expanded on it, made it more general, and implemented it in Python. Let's say we have a set of n minimum points, represented as y_minima equals y_1 foot, y_n, and the corresponding set of points where these minimums are achieved, represented as x_minima equals x_1 foot, x_n. We'll use a function similar to the probability density function, PDF, for the beta distribution when its parameter, alpha, equals 1. Initially, we'll support this function for any closed interval from C to C, where C is any real number. This function has some great features. Like the PDF, it can be extended to support any interval. We can control its differentiability through the beta parameter. It can be implemented efficiently, as shown by our PyTorch implementation. Plus, it's easy to visualize, which helps us understand the tasks better. We can support any interval by specifying the location and scale parameters, a and b. This is a general approach that works for any PDF or similar functions. We can define a function, h, that supports a closed interval of the form a, b** c, a plus b** c. This transformation is similar to the one performed in the PDF of the Laplace distribution. It flips the graph over the y-axis, resulting in a function that looks like the PDF of the Laplace distribution. The function h has a unique maximum at x equals a, and its differentiability is still controlled by beta. Given the set of minimum points y_minima and the corresponding points x_minima, we can create a function that satisfies the requirements by combining functions linearly. Here, b is half of the smallest distance among all distances between points in x_minima. We can also ensure that y_minima are the local minimum points. To do this, we introduce a parameter that is greater than any minimum point. We can adjust this parameter, c, but for our purposes, we can use c equals 1. This ensures that r is greater than any point in y_minima. We can then use r to add a negative factor to every function in the sum. This results in a function that guarantees the minimum points will be achieved at the given points. These minimum points will necessarily be the local minimum points. There is only one global maximum point, achieved at r in this study. We set c equals 1 and beta equals 2. The figure shows plots of such functions with various numbers of minimum points. There are other ways to construct functions with any number of minimum points. Implementing these functions and evaluating their performance could be a potential future research direction. In our experiments, we used 4 GPT-2-based models from Hugging Face. The table lists the models. Note that the number of parameters was affected by safetensors, resulting in higher parameter counts for the models than they would have been without safetensors. The maximum context size for all of the models was set to 1024. The context was fully utilized in the experiments. For the baseline model, we chose a two-layer neural network, 2NN, with 100 intermediate features and ReLU activation function. For training and evaluation, we used mean squared error loss, MSE, as the loss function in all of our experiments. We used AtomW as the optimizer with a learning rate of 0.0001. We varied the number of minimum points in the generated functions and evaluated functions with 1, 2, 3, and 4 minimum points. The number of shots was also varied and included 8, 16, and 32 shots. Inputs were sampled from the Gaussian distribution with mean 0 and standard deviation 1. Every LLM model was trained and evaluated on datasets of equal size. In all cases, the training was done for 1000 epochs. The table lists the hyperparameters. The hyperparameters for 2NN were the same as those for the transformer-based models and are shown in the table. Training and evaluation datasets were also the same. For more information about the training and evaluation setup, see the appendix. All trainable layers for the models were reset before training, so none of the GPT-2-based models had any pre-training or warm starting advantage. The training jobs were run on a single Quadro RTX 8000 GPU. The experimental results presented in the study can be reproduced on the same or similar GPU in approximately 3 hours. Section Summary. The authors propose a method for creating a parametrized function with a varying number of minima by combining simple functions through a linear combination. They demonstrate that this approach allows for easy extension to support arbitrary intervals, control over differentiability, efficient implementation, and visualization. The method guarantees that the specified minima points are achieved and are local minima, with a unique global maximum achieved at a specified point. Section. Results. Let's delve into our findings, which we've divided into 2 parts, the training phase and the evaluation phase. During the training phase, we'll look at loss graphs, discuss how the training progressed, and compare mean squared error, MSE, values. In the evaluation phase, we'll directly compare MSE values using the evaluation data. It's important to note that we used a Gaussian distribution with a mean of 0 and a standard deviation of 1 to sample both our training and evaluation data. In the training phase, we examined the results across different model types, the number of prompts, and the number of minima. For the Pico model, we found that increasing the number of shots led to a decrease in loss and improved convergence. This was also true for the 2NN model. However, increasing the number of minima had only a slight effect on the rate of convergence or the final MSE values. In all our experiments, the Pico model's MSE loss decreased much faster than that of the 2NN model, resulting in a lower overall MSE. The Tiny model showed even faster convergence than the Pico model, resulting in even smaller MSE values. The number of minima didn't significantly impact the convergence, but increasing the number of epochs led to a decrease in the overall MSE value. The small model followed a similar pattern to the smaller models, with a faster decrease in loss than the 2NN model, resulting in even smaller MSE values. Generally, increasing the number of prompts led to a decrease in MSE. The rate of convergence and the overall MSE were similar, regardless of the number of minima. The standard model exhibited the same behavior as the previous models, with a faster rate of convergence and smaller loss values. Changing the number of minima didn't result in significant changes in the rate of convergence or the overall MSE. The loss decreased as the number of prompts increased. In summary, our method proved to be resilient against increases in the number of minima. It also showed impressive convergence across all experiments. In the evaluation phase, we observed that as the number of prompts increased, the evaluation loss decreased for the Pico model. However, this wasn't the case for the 2NN model. Increasing the number of minima led to an increase in MSE and a decrease in overall performance. The Tiny model behaved similarly to the Pico model but with smaller loss values. The small model showed even smaller loss values and better overall performance. The standard model had the best overall performance, with a decrease in MSE as the number of prompts increased. Overall, the best performance was achieved when approximating a function with 1 minima. As the number of minima increased, the MSE values increased, and the performance declined. Increasing the number of prompts led to a decrease in MSE. The smaller training loss may be due to faster convergence. Our study has some limitations that could open up avenues for future research. For instance, we constructed a function in a specific way for our study. Exploring other methods for building functions with an arbitrary number of minima could be an interesting future research direction. Other hyperparameters could also be explored. Constructing out-of-distribution prompts for evaluation could provide further insights into the robustness of our method. Given sufficient resources, it could be worthwhile to consider larger transformer-based language models. Incorporating prompting approaches beyond input-output may yield promising results. Finally, the ability to generate functions with given minima also allows for defining new tasks.